Sorting in DBMS is important for two reasons. Output can be displayed in sorted order. Several relational operations can be implemented efficiently if input relations are first sorted. We can sort a relation by building an index on the relation and then using that index to read the relation in sorted order. This is expensive as number of records can be much larger than number of blocks. For this, it is desirable to order the records physically. The sorting can be applied to the relations that fit in main memory and to the relations that do not fit in main memory. For relations that fit in memory, techniques like quicksort can be used. For relations that do not fit in memory, external merge sort is a good choice. External merge sort. The external sort merge algorithm is explained here. The first step is create sorted runs. Let I be 0 initially and repeatedly do the following till the end of the relation. The first step is read m blocks of relation into memory. Here it is explained in this diagram. Read m blocks of relation into memory, sort the in-memory blocks and write sorted data to run Ri and increment the I value. Let the final value of I be n because we are sorting and doing the algorithm for n way merge. The second step is merge the runs. Here we have some steps. We assume that n is less than m and we are using n blocks of memory to buffer input runs and 1 block to buffer the output. And repeat the steps. That is, select the first record among all buffer pages and write the record to the output buffer. If the output buffer is full, write it to disk. Delete the record from its input buffer page. If the buffer page becomes empty, then read the next block to the run into the buffer until all input buffer pages are empty. And the third step is if I is greater than or equal to m, several merge passes are required. In each pass, contiguous groups of m-1 runs are merged. For example, if m equal to 11, then there will be 90 runs. One pass reduces the number of runs to 9 and each 10 times the size of the initial runs. Repeated passes are performed till all runs have been merged into one. Here, the output of the merge stage is the sorted relation. In this figure, it shows the example of external sort merge. Here, it is assumed that only one tuple fits in a block. And memory holds at most 3 page frames. During the merge stage, 2 page frames are used for input and 1 for output. The number of blocks transfers required for the external sort merge are computed as let the BR is the number of blocks containing records of relation R, and the first stage reads every block of the relation and writes them out again, giving the total of 2 BR disk accesses. The initial number of runs is BR divided by m. Since the number of runs decreased by a factor of m-1 in each merge pass, the total number of merge passes required is log m-1 BR divided by m. Each of these passes reads every block of the relation once and writes it out once, with two exceptions. First, the final pass can produce the sorted output without writing its result to disk, and second, there may be runs that are not read in or written out during a pass. The total number of disk accesses for external sorting are BR of 2 C of log m-1 BR divided by m plus 1. This is all about external merge sort. Now we move on to the join operation. In this section, we study several algorithms for computing the join of relations and we analyze their respective cost. Now consider the expression depositor join customer. We assume the following we will implement joins with the different algorithms, that is nested loop join, block nested loop join, index nested loop join, merge join and hash join. First we move to nested loop join. Here this algorithm shows a simple it is a simple algorithm to compute that theta join of two relations R and S. This algorithm is called as the nested join algorithm, since it basically consists of pair of nested for loops. Relation R is called the outer relation and relation S is called the inner relation of the join. The algorithm uses the notation TR dot TS, where TR and TS are the tuples. TR dot TS denotes the tuple constructed by concatenating the attribute values of tuples TR and TS. The nested loop algorithm requires no indices. It is expensive, and since it examines every pair of tuples in the two relation, and let us consider the cost of the nested loop join algorithm. The number of pairs of tuples to be considered is NR into NS, where NR denotes the number of tuples in R and NS denotes the number of tuples in S. For each record in R, we have to perform a complete scan on S. In the worst case, the buffer can hold only one block of each relation. Total NR into BS plus BR block accesses would be required. BR and BS denote the number of blocks containing tuples of R and S. Now we can let us consider the natural join of depositor and customer. Assume that depositor is the outer relation and customer is the relation in the join. We will have to examine 5000 into 10,000, that is 50 into 10 power 6 pairs of tuples. In the worst case, the number of block accesses is 5000 into 400 plus 100 disk accesses with the depositor as outer relation, and we can read both relations only once in the best case scenario and perform the computation. This computation requires at most 100 plus 400, that is 500 blocks accesses. The next one is block nested loop join algorithm. This algorithm, which is variant of the nested loop join, where every block of the inner relation is paired with every block of the outer relation. Within each pair of block, every tuple in one block is paired with every tuple in the other block to generate all pairs of tuples. All pairs of tuples that satisfies the join condition are added to the result. The difference in cost between the block nested loop join and the basic nested loop join is that in the worst case, each block in the inner relation is read only once for each block in the outer relation instead of once for each tuple in the outer relation. In the worst case, there will be total of BR into BS plus BR block accesses. BR and BS denotes the number of blocks containing records of R and S respectively. and in the worst case we have to read block of customer once for each block of depositor. The performance of the nested loop and block nested loop procedure can be further improved if the join attributes in a natural join or an equi-join form a key on the inner relation. Then for each outer relation tuple, the inner loop can terminate as soon as the first match is found, and reuse the block stored in buffer, which reduces the number of disk accesses that is needed. If an index is available on the inner loop join attribute, we can replace file scans with more efficient index lookups. The next one is indexed nested loop join. In a nested loop join, if an index is available on the inner loop's join attribute, index lookups can replace file scans. And for each tuple tr in the outer relation R, the index is used to look up tuples in S will satisfies the join condition with tuple T. This join method is called as an indexed nested loop join. It can be used with existing indices. And for example, shall we consider a depositor joins customer. Suppose that we have a depositor tuple with the customer name John. Then the relevant tuples in S are those that satisfies the selection customer name equal to John. So the cost of an indexed nested loop join can be computed here. For each tuple in the outer relation R, a lookup is performed on the index for S and the relevant tuples are retrieved. Then disk accesses BR are needed to read relation R, where BR denoted the number of blocks containing records of R. And for each tuple in R, we perform an index lookup on S, and the cost of the join can be computed as BR plus NR into C, where BR is the number of records in relation R and C is the cost of a single selection on S using the join condition. Here we in index nested loop join, we consider the depositor join customer with the depositor as the outer relation. Suppose the customer has a primary B plus 3 index on the join attribute customer name, which contains 20 entries on an average in each index node. And since customer has 10,000 tuples, the height of the tree is 4. And one more access is needed to find the actual data. The depositor, since the depositor is 5,000, the total cost is 100 plus 5,000 into 5, 25,100 disk accesses is needed. This cost is lower than the 40,100 accesses needed for block nested loop join. So CPU cost likely to be less than the block nested loop join. Then we move on to merge join. The merge join algorithm, also called as sort merge join algorithm, can be used to compute natural join and equi-join. Here let me consider R intersection S denote their common attributes. The algorithm is as follows: sort both relations on their join attribute and merge the sorted relations to join them. It can be used only for equi-joins and natural joins. Each block needs to be read only once. Thus number of block accesses for merge join is BR plus BS. If the relations are in sorted order, the number of block accesses is equal to the sum of the number of the blocks in both files BR and BS. In the algorithm, join attributes refers to the attributes in R intersection S and TR joins TS, where TR and TS are the tuples that have the same values for join attributes, and denotes the concatenation of the attributes of the tuples followed by projecting out repeated attributes. The merge join algorithm associates one pointer with each relation, and these pointers point initially to the first tuple of the respective relation. As the algorithm proceeds, the pointer moves through the relation. A group of tuples of one relation with the same value on the join attributes is read into S, and the algorithm records the every set of tuples S fit in memory. So the block access is BR plus BS. The next topic, hash join. The hash join algorithm can be used to implement natural joins and equijoins. In the hash join algorithm, hash function is used to partition tuples of both the relations. And the basic idea is to partition the tuples of each of the relations into sets that have the same hash value on the join attributes. Let us assume that hash function mapping join attribute values of 0 to n, and join attributes denotes the common attributes of R and S used in natural join. HR denotes the partitions of R tuples, each initially will be empty. HS denotes the partition of S tuples, and this also initially empty. The idea behind the hash join algorithm is that R tuple and S tuple satisfies the join condition. They will have the same value for the join attributes. If that value is hashed to some value I, the R tuple has to be in HRI and the S tuple in HSI. Therefore, R tuples in HRI need only to be compared with S tuples in HSI. They do not need to be compared with S tuples in any other partition. If D is a tuple in depositor and C is a tuple in customer, H is a hash function on the customer name attributes of the tuples, then D and C must be tested only if H of C is equal to H of D. If H of C is not equal to H of D, then C and D must have different values for customer name. Customer name. If H of C is equal to H of D, we must test C and D to see whether the values in their join attributes are the same. Since it is possible that C and D have different customer names that have the same hash value. This is the algorithm for hash join to compute the natural join of relations R and S. So this is all about hash join algorithm. Thank you.